Hello and welcome to the online lab on emulsions as part of the Formulations lab series. So this lab is going to be given to you pre-recorded by me in my kitchen, and then you're going to be able to do these practical parts that illustrate the theory that I'm going to talk you through in a moment yourself at home in your own kitchen or on any table anywhere. And to do that, you're only going to need to use things that are freely available in homes: a bowl, some spoons, some glasses, some water and some oil. That's all you're going to need, and with that you'll be able to see in reality what the theory is that I'm talking about through this lab about emulsions. So I'm going to do the practical part as well on camera with you, but you don't have to use exactly the same as me. You can substitute anything in that you need, that you've got, and to just have a look at the theory of this in practice. I'm aware that doing labs at home might not be the easiest thing in the world, and particularly if you've got younger people around you, maybe younger siblings or children. So if you want to get them involved in doing this, everything we're using is completely safe, and so you can definitely get them involved in it. And whilst I'd suggest that you use the proper lab script for this, there is available a sort of simpler version under my website called the Kitchen Lab, which has got a whole load of different labs that are made specifically for children, and they could follow along using the script from there. And there'll be links for that in the video, underneath the video, and also in the folder where this came from as well. So do get them involved and carry on, and feel free to have a look through the website and see if there's any other labs that you want to do with them as well, and homeschool experiments. So to the lab. I'll be going through some of the background and theory first, then I will be doing the practical part myself, and then I will cut away and look at some of the analysis, a little bit of calculation, and putting this theory into the pharmacy practice as well. So we're going to learn how to prepare an emulsion, and we're going to learn how to stabilize an emulsion. So you're then also going to learn the theory of HLB. That's hydrophilic lipophilic balance, and that's a measure we look at surfactants with, and we're going to look at those values, how we can manipulate those values, and learn about their effect on stabilizing emulsions. So you're going to prepare some emulsion formulations at home and see how good or bad different surfactants you have at home are at stabling emulsions. In this lab, I will talk about emulsions, which are specifically two immiscible liquids being dispersed through one another. They are an example of a colloid, but a colloid is a more general term that describes any stable suspension of one type of matter through another. So for example, a cloud is a colloid of liquid in gas, and a sponge cake of gas in solid. But today we're specifically talking about emulsions, which specifically refers to two immiscible liquids, one being suspended through the other. So we might also call that a disperse system, where we've got these two immiscible liquids, one being dispersed through the other. And we would have a minimum of two phases in an emulsion. We can get more complicated, and we can start to have more than two different immiscible liquids, and that's something that maybe you would come on to later. But essentially, we take one of those immiscible liquids and form it into tiny droplets, small enough that they're homogeneously dispersed through the other liquid. And we, again, similar to a suspension, would call the bulk liquid, the one that there's more of, the continuous phase, and the other liquid, which there's less of, which is in small tiny droplets, the disperse phase, because that one is dispersed through the continuous phase. Simply speaking, with emulsions, and generally what you will class them as, will either be a water in oil emulsion or an oil in water emulsion. A water in oil emulsion gives fine aqueous drops dispersed in an oily continuous phase. So in a water in oil, we have water droplets in oil as the continuous phase. Whereas an oil in water emulsion, we have oil droplets dispersed through a water continuous phase. So we have fine oily droplets as the disperse phase, and we have water as the bulk continuous phase. So you'll know from your own experience that if you put oil and water together, you get two layers, much like we have here in this jar. So you can see we've got water at the bottom and we've got oil at the top, and they've separated, and oil in this case is less dense, so it's gone above the water, which is more dense. Because they don't like each other, they're immiscible, so they form two phases. And this reduces the surface area between the two liquids to its minimum, which reduces their contact. And that also reduces the energy in the overall system to its absolute minimum. So this, where they've completely split, is the most thermodynamically stable state for these two liquids to exist together. So how then can we take one of these liquids that really doesn't want to be touching at all the other and force it into tiny droplets and keep them suspended through the other liquid? And in the lab today, we're going to be looking at oil in water emulsions as our examples. So if you were to mix this oil and water vigorously, you would, for a short time, see that we get an emulsion. So if I mix it, you can see that we get a cloudy liquid there in one phase, and that is a very short-lived, very unstable emulsion. But you can see very quickly now that it started to go back into two layers. Got the oil on the top, and now the clear water forming on the bottom again. So we managed to get them into one another very briefly, and we've done that by mixing, and there we've put energy into the system to form oil droplets. This, however, has increased the area of the oil and water interaction, and the smaller the droplet we formed, the larger the contact between the oil and the water, and the larger the contact angle between the oil and the water. Because it's smaller, we've got a higher angle between the water and the curve of the oil droplet. So we've got more oil-water interaction, and we've got a higher angle of contact between the two of them. And this gives us a much higher interfacial tension and means that there's a lot of energy in that system. And so by mixing, we've produced a higher system energy. And remember, things will always tend towards their lowest system energy. And so very quickly, those droplets will agglomerate, coming together, which will lower the angle at which those two phases are meeting, and it will reduce the amount of interfacial area and the interfacial tension, and therefore the energy. And as that agglomeration becomes more and more and more, we get a bigger and bigger droplet, which lowers the tension even more, all the way to its end point, where it's gone completely flat, and we've got complete separation between the oil and the water. So therefore, to keep those droplets in there longer, what we need to do is lower the interfacial tension between those two phases, so that the driving force for it to split again is reduced, and the droplets can last longer. And the way we do that is with surfactants. So you've already seen in the first lab in this series that surfactants form micelles in water, as they are amphiphilic. And for a more detailed explanation of that, please go back to the first lab. In an emulsion, the surfactants that we know will form micelles will surround those oil droplets, as long as they're past their critical micelle concentration. And their hydrophobic tails will go into the oil droplet and dissolve in there, and their heads will poke out into the water, and they will surround the oil droplet. So this is almost protecting that oil, so it doesn't really have to interact with the water at all. And that reduces the interfacial tension between the two and stabilizes those smaller oil droplets, which allows us to make a stable suspension and a stable emulsion where we have small oil droplets dispersed through another immiscible liquid, in this case water, and the surfactants reduced that surface tension. It's almost protecting the oil from the water so much that we get a stable emulsion of one phase dispersed through another immiscible phase. And you can see a visual representation of that in the lab script. So by using energy to form very small oil droplets, which we can do already, we can use energy to form very small oil droplets and create this white looking single liquid. But we know that that's very quickly going to split again. By adding in a surfactant to the system to reduce that interfacial tension, we can add that same energy in again to create those small oil droplets and stop them from going back to splitting by reducing the interfacial tension. And in that way, we can create a stable emulsion. Now, this is exactly what you were doing when you use washing up liquid to remove grease from your dishes. So you put in surfactant in, fairy liquid or whatever it is you're using, and that's forming micelles, and it's going to then take those oil droplets that you're making by scrubbing the dish and stabilize them in the water, making grimy looking dishwater that you can simply pour away down the sink. So as surfactants help to make emulsions, we might also call them emulsifiers. But a surfactant is a specific type of emulsifier. There are other things that could be used as emulsifiers that aren't surfactants, such as clay minerals or proteins. So we're using surfactants, which is one example of an emulsifier, but there are other emulsifiers that can also be used to perform the same role. Now, specifically with surfactants, we might want to measure how good they are at stabilizing different types of emulsion. I already mentioned that we have water and oil emulsions, and we have oil and water emulsions. We may also have more complex multi-phase emulsions. For example, oil in water in oil. So we'd have droplets within a continuous phase. And when we start looking at those sorts of systems in particular, we have to start being very careful about the surfactant we use. And different surfactants are more suited to stabilizing different types of emulsion. One of the most common ways of selecting the correct surfactant or mix of surfactants is by looking at something called their hydrophilic lipophilic balance number, which I will refer to as HLB. Hydrophilic lipophilic balance number. So HLB values are a measure of the balance between the hydrophilic part of a surfactant and the hydrophobic part of a surfactant. These values range from 0 to 20, and it's an arbitrary scale. And each surfactant or emulsifier has a unique HLB value. So the higher up the scale you go, so typically if it's over 10, if a surfactant has an HLB value of over 10, that indicates that we have a hydrophilic surfactant. So one where the hydrophilic part of the surfactant, of that two-sided molecule, is much bigger. So generally it would prefer to be in water. And then when we go lower down that region, particularly to sort of below 6, we get the lipophilic, oil-loving surfactants, where there's a longer lipophilic, oil-soluble part, and so generally they would prefer to be in an oil. And the uses of those may differ. The more hydrophilic, water-soluble surfactants we would like to use when we're going to have a water continuous phase. And they will be what you will find in your detergents and in your shower gel. Then we might have sort of somewhere in the middle, where we may use them as wetting agents, much like we did in the suspensions lab. We had a wetting agent, they're about 50-50. All the way to the hydrophobic ones, predominantly hydrophobic, with an HLB of between sort of 0 and 6, where we might use those as anti-foaming agents to stop things from foaming up. So we don't necessarily want to do much with it, we just want to stop bubbles and foam forming on the top of a liquid. And there's a figure in your lab script where you can see that sort of laid out visually. Now, we don't have surfactants that fill every single number within the HLB scale. And so what we will do to try and get the exact number is use a mixture of different surfactants. And they will work in an additive way to get to the final number that we actually want to stabilise our emulsions just how we would like to stabilise them. And the HLB value that we arrive at when we mix surfactants is simply a factor of how much of each we use. So the relative amounts of each surfactant we use will directly influence the final HLB value that we get. And there's a formula for determining what the final HLB value of a mix of surfactants will be. And that states that the HLB of the mix is equal to the fraction of surfactant A times the HLB of surfactant A added to the fraction of surfactant B times by the HLB value of surfactant B. Maybe that makes sense to you. So essentially, we take a decimal fraction of how much we've got of each. So if we had 50-50, we were putting half of each surfactant in, we would have 0.5 times HLBA plus 0.5 times HLBB. If we were putting in 75% of A and 25% of B, we would have 0.75 times HLBA plus 0.25 times HLBB. Hopefully that makes sense why that is. And if you were to think of it on a number line, if you had a surfactant which had an HLB value of 5 and one that had an HLB value of 10, and you mix them in a 50-50 ratio, you know you'd get to 7.5 because that's the average of the two. If you had those same two, 5 and 10 again, and you put in a mix of 20% of one of the lower value and 80% of the higher value, you know that we'd have a value, an HLB mix of 9, because that's 80% between the two, towards the one we've got more of. And that's all that this formula is doing. It's just putting that into mathematical language. And later on, once we've done the practical part of this lab, we'll be looking at how you manipulate that formula and how we can use that to determine how much of two surfactants we would need if we have a set HLB value we're trying to reach. Without having to do trial and error, we can just mathematically rearrange this formula to tell us how much of each we need. And we'll be doing that after the practical part. So in addition to the use of emulsifiers to stabilise droplets in an emulsion and modify their interfacial tension and agglomeration, there are other factors that will affect their behaviour. These are very similar to those factors that we spoke about earlier in the suspensions lab. So once again, we're looking at Stokes Law, and we'll see how Stokes Law can affect droplets and their sedimentation or their agglomeration and then eventual creaming or sedimentation, splitting. But this time it's in a slightly different form. And again, you don't need to learn this equation, but hopefully you can see that equation on there and see that it's actually basically exactly the same. We've just replaced particles with droplets, essentially. And instead of a solid particle being dispersed, we've got a droplet of the dispersed liquid. And V becomes the rate of separation rather than just the rate of change for sedimentation of a suspension. So those same factors are still at play, but we can also talk about reducing interfacial tension with a surfactant when we're using emulsions as well. So, to the practical part of the lab. That's kind of the background, all of the theory that informs how we look at emulsions. And the practical part today, you're going to be doing yourselves at home. So I will call this a kitchen lab. So you're going to be making a few different emulsions using some household materials and seeing if there's any difference between them. I've put a list of what you need in the lab script, And as I said, if you don't have those things exactly, don't worry, substitute as you've got and see how you get on. You'll be able to see what I did with those exact pieces of equipment or kitchenalia in the video now as well. Okay, I'm actually set up now. So in the first part of the practical of this lab, we're just going to show, and you can see exactly how oil and water don't mix. But we'll also be making a control for the other parts of the experiment we'll be doing later. So do this part. So first of all, you've been asked to just pour some water into a small glass or bottle. And I'm just going to fill it about half the way up, which is around about 80 millilitres. And then you've been asked to add 2 spoonfuls of oil. 2 dessert spoonfuls of oil. So I've got a dessert spoon here, and I'm going to put 2 of those. This is just sunflower cooking oil, sunflower oil. And I'm just going to add 2 of those into this glass here. Okay. And then I'm just going to take a smaller teaspoon so it can be mixed. You should be able to see that the oil is floating on top of the water, just as we showed with the oil and water in a jar earlier. So we're then going to mix this just as hard as we can within the glass, and you'll see that those 2 layers, once the vortex has gone, will separate out again very quickly and easily, like so. This is because oil and water are insoluble in each other, and they won't mix, as we've already explained. So they're going to return to their lowest energy state, minimizing their contact between each other, and separate out. Have a think about how they split, and earlier I mentioned about density. So what does this experiment tell you about the density of oil and water? We've got oil on the top and water on the bottom. So the next step in the lab is we're actually going to force these to mix. We're going to keep this one separate as a control to come back to later, but now we're going to force some oil and water to mix. So again, take your dessert spoon, which you've used with oil, and pour 2 dessert spoons of oil into a round bowl. Any bowl will do, but as round as it can be will help with the mixing stage in just a moment. We then need to put in 2 teaspoons, I'll use a different teaspoon here, of a liquid surfactant. So you can use anything. So I've got a few here. I have got my shower gel. I have got my laundry detergent. And I've also got my washing up liquid. And so I'm going to start with my washing up liquid. I'm going to put 2 teaspoons of that into this oil. It's a bit viscous, so just bear with me. Okay. So 2 teaspoons of my washing up liquid, my surfactants, are now in with the oil. If I readjust the lighting, you should be able to see that. There we go. So I've got oil and some liquid soap in there. And then we need to mix these 2 together really, really well in a circular crushing motion. So in the last lab, I spoke about holding your pestle and mortar like a pen. This is the part of the lab where you would hold it very firmly in your fist and really get in there and go round so you can use the arm muscles rather than just the wrist muscles. But I'm sure that not everyone has a pestle and mortar at home, so we're going to do that using a bowl and the back of a spoon. Okay, so we're going to do that with a circular crushing motion using the back of the spoon. And what you should notice is that you start to get a very white creamy looking liquid. And if you've got enough of it in there, you'll notice a little clicking sound, like a little, which I can hear now. I'm not sure if you can pick it up on there. As the back of the spoon comes around the bowl, if you're going fast, you should hear a sound, okay? If you don't worry, but that is a suggestion that you are forming a good emulsion. That clicking noise is a suggestion that you've got a good emulsion, okay? So give that a really good crushing mix with the back of a spoon. You can go up the side of the bowl, and this is where having a bowl with high sides is very useful. That's why I'm using a round kind of bowl. Okay, and you will hopefully develop this white, opaque, milky liquid. Okay, so once you've done that and you've mixed it well enough, we're then going to add in 1 dessert spoon of water. And again, using the back of our teaspoon, we're going to very quickly do exactly the same mixing that we've just done. And hopefully it all stays together in one phase. You might need to do this for a little bit. And you will form still a milky white liquid, we hope, but much looser. And you might start to see a little bit of splitting of the oil and water, depending on the soap you've used. Hopefully not. So now what we're going to do is we're going to put that into a glass, a similar glass to the one we used for just the oil and water. Excellent. And we're going to want to add in a similar amount of water to that which we used before, so we can compare them. And again, I spoke about a multiple rinsing technique last time. That's exactly what I'm going to do again here, so I can get everything out of that bowl into the final vessel until we've got around about the same volume. And then once more, give it a really good stir. Okay. Now, albeit in a rather bucket chemistry way, what we've done here is exactly the same theory as what we would have done in the lab. We've made what hopefully is a relatively stable emulsion. And if I hold them up to the camera, you can see here that we've got the milky, white looking liquid in one phase, and we've got the clear water and the clear oil in 2 phases. And the difference between those is the surfactant we've added, and also the technique by which we made it. That technique was quite key. That crushing motion that we used was key in forming those small droplets that could then be stabilised by the surfactant. If we just put the surfactant in and didn't mix it thoroughly and didn't make that crushing motion to make those small droplets, we'd be starting out with large droplets still, which would still want to separate much faster. We need to make droplets that are so small that the force of all of the water molecules hitting it can overcome gravity and the density difference between those two and stop them from splitting so fast. And so we simply get one homogeneous oil in water emulsion. But I know that that's not going to stay homogeneous for a very long time. And that's because the surfactant we use may not be the right surfactant. We may not have had the right HLB for it, because each of these surfactants have been made to do different jobs and designed specifically to get the right HLB for that. So that moves us on to step 4 in your lab script, which is to ask the question, are different soaps better than each other? So eventually the oil will separate from the water, okay? We're slowing it down dramatically, but it will eventually separate. And in fact, you may be able to see this starting to separate here now. If I put a bit more backlight on, you can see that there's 2 layers that are forming here. So we're getting some creaming there with the oil going up to the top. And how fast this happens depends on how we design our emulsions and what soap you've used. It's also going to depend on the droplet size you've made. So maybe you can make these last longer with a more vigorous mix. It's also going to depend on the liquid densities. So maybe if you use a different type of oil to me, you're going to find that your separation happens at a different speed as well, because you might have a more or less dense oil. And it's also going to depend on the continuous phase viscosity and density. But we're using water, and I think that will remain pretty similar for all of us. And so now what we can do is we can repeat this same method with our different soaps. And we can see which one is best at forming an emulsion in a glass like this. And if we give them all a good mix at exactly the same time, we'll be able to monitor which one creams and splits first, which one lasts longest, so you can see which of your surfactants that you've used is better at stabilising this sort of oil in water emulsion. So I'm going to make up a few more of these just off camera, and then I'll be coming back and we'll be able to see the results next to each other. I've now made up 3 different emulsions. You can see here in front of you, from left to right, we have got laundry liquid on the left. We've then got shower gel next, then the washing up liquid, and finally the last one you can see, of course, has no surfactant in whatsoever. Now, the first thing that you might notice is that no matter what colour those different detergents were, those different surfactants were, we had sort of a yellowy colour, a green colour, and a clear, no colour. We've got white emulsions that have come out of it. So I wonder if you thought why that might be. And that's because, well, it's a good sign that we're making droplets that are very small. So hopefully when you mixed your surfactant in with your oil, your soap in with your oil, you noticed that after a few mixes, it went this sort of white creamy colour. And that's because the droplet size is so small that rather than absorbing and reflecting light like bulk materials tend to do, how we're used to seeing materials interact with light, like these tiles being different colours and this being black absorbing all the light, these have gone so small that they're approaching the same sort of size range as the wavelength of light, of different lights. And so instead of absorbing and reflecting, what they're doing is they're scattering the light. So they're just scattering all the light that comes to it in all directions, which means that we see all of the wavelengths, which means that we see white. So rather than being coloured, we see them as off-white. And that's because they are scattering the light rather than absorbing it and reflecting it. And that's the same reason that milk is white. If you've ever seen milk split, it splits into a clear phase and then an oily yellow phase. But milk itself is white, exactly the same reasons. Now, whilst I've been talking, hopefully you've been able to see that these emulsions have started to split. So whilst they were all freshly mixed, just as I came on, you can see that the washing up liquid, part 1 on the right here, has almost completely split. We can see that the shower gel here is well on its way to splitting just as much, and that the laundry detergent has barely split at all. We've got a very stable emulsion, I believe, from the laundry detergent. In fact, no, we haven't. No. If we look closer, that's just a trick of the light, the angle. We've got the oil phase on the top still, and we've just got a cloudy emulsion still in the bottom. But we've probably got more of an emulsion going on here than we do in these two here. So for making this sort of emulsion, this oil and water emulsion in this kind of in a glass like this, the laundry detergent has performed best. Now that may be because its HLB number is more appropriate. In this experiment, it may just be that it was more concentrated. And so whilst we put the same number of spoons in of each one, there may actually be more surfactant molecules going into that. But we can see, though, that these weren't stable for a very long period of time. So none of them were particularly appropriate for making a drink, for example. If we wanted to turn these into a drink that you could have, or maybe in liquid oral dosage form, for example, then none of these surfactants would have had an appropriate HLB to do so. And so we may use something more like you see in the lab script. We may use a mixture of tween and span, for example, rather than what's in these detergents, which is most likely sodium dodecyl sulfate. That's most likely what's in these. So these are perfectly fine for their use in the house, which is to simply wash away oils. And so for those, it doesn't need to create a long-term stable emulsion. It just needs to be long enough for you to wash the oils away, be that off your clothes, off your body, or off your dishes. And so you can see here the influence of different HLB numbers and different types of surfactants and emulsifiers, and getting the right one for the right job, because here they're not appropriate, and hopefully we would be able to make something that is appropriate. Hopefully you can now see how different soaps will affect emulsions that you produce, and that some are better than others for doing different jobs for making emulsions and making them stable enough for the jobs that we want. But say, for example, you were given an emulsion and you weren't sure what sort of emulsion it was, whether it was simply an oil in water or a water in oil emulsion. How would you be able to tell those two apart? Because they both look like creamy white liquids. And depending on the oil that's being used, it may have a similar viscosity and density to water. So there's another couple of ways that you can, a couple of techniques you can use to be able to tell an oil and water and a water and oil emulsion apart. The first of which you could try at home yourself, which is a dilution test. And typically it would be a water dilution test because that's what we'd have around. And simply, you just take the emulsion, dilute it with some water and see what happens. If the emulsion readily dilutes with the water, then you know you have an oil in water emulsion, because the water will be the continuous phase and all you're doing is increasing the continuous phase. If, however, you put that water in and it didn't mix, you got a lumpy mixture, or it simply just sat underneath it or sat on top, you'd know that you had a water in oil emulsion. And that's because the continuous phase there is oil. And you may just have put too much water in and split the emulsion, cracked the emulsion, or you may just not mix with it. So the dilution test, if an emulsion readily dilutes with water, it's an oil and water emulsion, and if it doesn't, it's a water in oil emulsion. And you can try that yourself at home using a bit of milk. See whether you think milk is an oil in water or a water in oil emulsion by diluting it with some water and seeing what happens. The other way that we may test is by conductivity. Now, you can't test this one at home unless you happen to have a multimeter to hand, but simply put, water conducts electricity slightly and oil doesn't. So if you put a probe, a conductivity probe into the emulsion and it conducts, then it's an oil in water emulsion, because the water will be the continuous phase and will be allowing some charge through. Whereas if it doesn't conduct at all, it will be a water in oil emulsion, because the continuous phase there is the oil and that won't conduct and it won't allow charge to go through it. Now let's look at having some numbers on all of this. I've spoken a lot about the theory behind it, And I hope you understand the theory behind that now, and you're happy that emulsions use surfactants to stabilize two immiscible liquids, one in the other, by reducing surface tension, and that the different surfactants we use are better for different jobs. And the major way we determine and classify those different surfactants is by using the HLB value, the hydrophilic lipophilic balance value. And now I'm going to put up on screen the lab script and a little blank page next to it, and we're going to look at HLB in a bit more depth because there are some calculations associated with that which you need to be able to perform. When we prepare an emulsion, we may need to reach an HLB value that is not available with the surfactant that we have. And so to reach these values, we use different surfactants that can be mixed together in precise fractions to get to that final value we want. And two really common surfactants that we will do that with are span 80 and tween 20. And that's because span 80 has an HLB quite low at 4.3, so it's very oil loving. And tween 20 has a very high HLB at 16.7, which means it's very water loving. And that means that with very precise fractions of each of the two of those, we can reach any HLB between 4.3 and 16.7. And when we mix surfactants, we assume that they're going to have an equal influence on the final HLB value. And so to determine the exact amount of each that we use, we need to rearrange equation 3.1 that you saw further back in the lab script. But before we get to that, let's change that formula slightly to how it's written in equation 3.3, where we've taken FB, the fraction of surfactant B, and changed that to 1 minus fraction of A. And this is where it's important that we use decimals, because this will only work if we use decimal fractions for this. We know that in total, the fractions of our surfactants should add up to 1, because that's the whole, that's the total. And so if we only have two surfactants, it stands to reason that 1 minus one of those fractions will equal the amount for the other fraction. It will equal the other fraction that we need. And that's put here in this text, maybe a bit more eloquently, but that gives us this formula here where we can determine the HLB of a mix of surfactants using just essentially fraction A, but fraction B is 1 minus whatever fraction A is. Now, a good tip here is to ensure that you set surfactant A to be the surfactant with the highest HLB value. This doesn't change the calculation. In fact, it would work either way. However, it does mean that you don't have to deal with negative numbers and you don't doubt yourself as you're going along. So let's just first do an example for how to use this straightforward formula to determine what the mixed HLB would be for two known surfactants in a known ratio at known different fractions. So here I would like to mix 1 part of tween 20 and 9 parts of span 80. And I'm going to set tween 20 as A because this has got the highest HLB value. This has got an HLB of 16.7, as we said, and I'm going to set B as span 80 because this has got the lower at 4.3. Now, if you're not happy to intuitively know the fractions that we're working with here, then, or maybe it's slightly more complicated numbers, then we can determine the decimal fraction of each part being used by dividing the number of parts for each surfactant by the total number of parts used. So in this case, for tween 20, for example, we're using 1 part. But in total, we're using 10 parts because that's 1 plus 9 parts. 9 parts span, 1 part tween. So in total, it's 10 parts. So the decimal fraction that we'd be using of that, of the tween 20, is 1 divided by 10, which is, of course, 0.1. So therefore, FA equals 0.1. Okay, we could do the same for B, which would be 9 divided by 10, which would equal 0.9. And here you can also see that 1 minus FA would also equal 0.9. So we can see that these are equivalent. you can get to the same number two different ways. So our little change in the formula here is absolutely fine. And so now all we need to do is substitute all of these values, these FA, FB values and HLB values into our formula. And this is what we get here, which would be 0.1 times 16.7 plus 0.9 times 4.3. But we're just doing this in this different form here, which is 1 minus FA. But we could just as correctly put that as saying 0.9 there. And if you do that calculation, you should get the answer 5.54. So that is a very straightforward use of this formula. But you're also going to need to be able to manipulate that formula to be able to determine the fraction of two surfactants to get to a final HLB mix value. And the rearrangement that we need to do for that is shown here. So we start out with the HLB mix equals fraction of A times HLBA plus the fraction of B, which is 1 minus FA, times HLBB. But we're just going to get rid, first of all, to do this rearrangement, we're going to get rid of these brackets. I should point out here, you don't need to be able to show me this rearrangement. I'm just showing it to you so you see where it comes from. You need to be able to use the formulas if you're given them, all right? So here's the rearrangement. We times out these brackets here, and we get HLB mix equals FA times HLBA plus HLBB minus the fraction of A times the HLB of B again. And then we can rewrite this without the brackets, which would then be HLB mix equals FA times HLBA plus HLBB minus FA times HLBB. We've just taken off the brackets there. Now we can get rid of HLB because we need to try and isolate FA. Okay, we need to try and isolate FA, the fraction of A, because then with that we can determine the fraction of surfactant A and the fraction of surfactant B that we need to use. So we first do that by taking HLBB from either side, which gives us HLB mix minus HLBB equals the fraction of A times HLBA minus FA HLBB. And then we can factorize this side of the equation, okay? Because we've got FA times HLBA minus FA times HLBB, which means we can take FA outside of a bracket, which means we've isolated it, which is what we want to do, leaving this form here, and then what's in the brackets can be divided by to get it onto the other side. And there we have isolated then FA. So if you didn't follow that, don't worry. I'm not going to ask you to show that. I'm not going to ask you to show that in an exam situation. And anyway, I couldn't because it's a multiple choice exam. So no problem there. But what you need to get to is you need to get to equation 3.4, which states that the fraction of A that we would need to reach a set HLB value is determined by the HLB mix that we want to reach, so our target value, take away the HLB value of our surfactant B, divided by the HLB value of A, take away the HLB value of B. Okay, so we've got two equations. We've got one equation, if you've got two surfactants and you know how much of each part you're putting in, you can determine what the mix, the final HLB value would be with this equation. And if you've got two surfactants and you've got a final target value of HLB and you need to determine how much of each one to put in to get there, we've got this equation here, which gives you the fraction of A that you need to get to there. And you can find out the fraction of B you need by doing 1 minus the fraction of A. Okay. And this is again why using decimal fractions is so important, because the sum of your two fractions of surfactant will equal 1. Now just remember as well, if you're asked for the fractions of surfactants needed, that's fine, you've got the answer. But if you're asked for the amount that you need to multiply the final mass of surfactant that you need by your two fractions to tell you the mass that you need of A and B. Okay, so that's a lot of things going around in your head maybe, so maybe pause and have a look and go back and go over that yourself. But then I'm going to go on now to do an example calculation of that. So we have span 80, again, HLB of 4.3, and tween 20, again, an HLB of 16.7. And we need to make 10 grams of surfactant mix with a target value of 8.4. So how are we going to work that out? Well, we're going to use this formula, of course, aren't we? And I need to know how much of A I'm going to put in. Now, again, I'm going to set A to be the one with the highest value, which is going to be tween 20. And I'm going to set B to be the one with the lowest value, which is span 80, just to keep the numbers easier. So the fraction of A we need is going to equal our target HLB, which is 8.4. And then we need to take away the HLB value for B, which is span 80. And so the HLB for B is 4.3. And then that needs to be divided by the HLB value for A, which is 16.7, minus the HLB value for B, 4.3. Now, here you can see why it was easier to set A as the one with the larger HLB value, because we're going to have nice positive numbers here. So let's do that calculation. What's 8.4 minus 4.3? So I guess that's 4.1. Yeah, that should be 4.1. And then that needs to be divided by 16.7 minus 4.3. So what's that going to be? 16.4, 12.4. So 12.4. 4.1 divided by 12.4, I believe. I am genuinely doing this calculation as I go. So if I make a mistake, I apologise. And in fact, let's check myself on the calculator. 8.4 minus 4.3 is 4.1. Perfect. And that's going to be divided by 16.7 minus 4.3. And so we reach a value of 0.33, etc. 0.33. So I know now that the fraction of A I need is 0.33. So that is the fraction of tween 20 that I need. And fraction of B equals fraction of A, equals 1 minus fraction of A, which is equal to 1 minus 0.33, which is equal to 0.669, so 0.67 to make this work. Okay, so that nicely adds up to 1, as it would do. So this is the fraction of span 80 that we need. And remember, we need to have how much of we're going to use for 10 grams. So for tween 20, we would then, for tween 20 here, we would then do, so mass of A is equal to 10 times 0.33, which means we're going to put 3.3 grams of tween 20. We're going to put 3.3 grams of tween 20 into our mix to get that final HLB value that we wanted, which was 8.4. And we can do the same with span 80. Now, again, there's maybe two ways of doing this, but we would do 10 times 0.67, which means that we're going to put 6.7 grams of span 80 in. Now, we could, if you follow it through in your mind, we could also just do 10 minus 3.3 here, because 10 is the final mass that we want, and we know we're putting 3.3 grams in of A, so the remainder must be B. So the final answer here then is we need to put in 3.3 grams of tween 20 and 6.7 grams of span 80 together to get 10 grams of a surfactant mix that has an HLB value of 8.4. Okay, so some of you will have followed that through perfectly first time. Some of you might struggle with that a little bit more. I know I struggled with that a little bit first time I did it, and it's just different people, different brains, horses for courses. If you're struggling with that, make sure you go over that a few times so you know how to do that. Okay, now you can sense check your answer, because if you were to put these values on a number line, like I said right at the beginning, you'd be able to estimate how much of each surfactant is needed anyway. And so if we put tween 20 and span 80 on this number line, we can see where in between we should get roughly. So for example, with tween 20 and span 80 again, if you were asked to get an HLB of 10.5, you could do all of this calculation and you could reach the value of F, the fraction of A and fraction of B would be 0.5 each. And you can see that because that value is exactly halfway between tween 20 and span 80. And so you can use this idea to sense check your answers. So for example, here we were asked to find an HLB value of 8.4. Now I know that 8.4 is closer to span 80. It's closer to span 80. So I should be putting in more span 80 than I am of tween 20. And indeed, if we were to put this, if we were to put these fractions on the number line, I'm putting in 0. If we put this on the number line here, so where is it? What was it I was saying? Yeah, 8.4. So we put that here, like at 8.4, we'd be able to see that I would need to have an awful lot more, because it's a lot closer, I'd have to have an awful lot more of span 80. And so confusingly, you get the fractions are sort of the opposite way round on the number line. Okay, so this isn't a way I'm going to suggest that you actually try and work out the answer. It's just a way of sense checking your answer. So if your HLB value of the mix is in the middle between the two, you should find that you're having roughly equal fractions. If it's much closer to one than the other, you should be having a larger fraction of the one that it's closer to. It's just a sense check that you can do visually on a number line. But this is how you would work it out. Okay, you would use this equation and then you would do this kind of working out over here. Okay, that's what you would do. So I'm going to now go through the practice questions that I've got on here for you. So you can go through them yourselves and you can test yourselves as you're going. So I suggest you try and do these questions on your own first, and then you come back to the recording and you can see how well you got on. So you have two surfactants and the HLB values are as follows. A is 5 and B is 18. You are required to mix them in a ratio of 0.3 to 0.7. What would the resulting HLB value be? So what would that be? So which formula are we going to use? Well, we're going to use this first formula here because we've got the ratios and we've got the HLBs. So all we need to do is put them into this equation. And so the HLB of the mix is going to equal fraction of A times HLB of A plus fraction of B times the HLB of B. And let's go back to that. Let's go back to the question. We've got A equals 5 and we're putting in 0.3 of it. So 0.3 times 5 plus 0.7 times 18, which is equal to 0.3 times 5 is equal to 1.5 plus 0.7 times 18 is equal to 12.6. So our HLB mix is going to be 14.1. Okay, now let's sense check that. We are putting in more of B, so our HLB mix should be closer to B. 14.1 is far closer to B than it is to A, so that makes sense. Okay, so let's move on to these further questions. Question 2. For the following questions, you're required to determine the fraction of each surfactant required to reach the target HLB. And you're also going to need to find the mass required to determine the mass of each. As a reminder, HLB values of span 80 are 4.3 and tween 20 is 16.7. So I'm not going to do all of these. I'm going to do one more of these and leave the others for you. So question 2, we want to get to a final HLB. We want to get to a final HLB of 9.5, and we need a mass of 10 grams. So we want to know how much of each we're putting in. So this is the formula we're going to use. We're going to find out how much of A we need to get first. So the fraction of A is equal to the HLB of the mix minus the HLB value for surfactant B over the HLB value for surfactant A minus the HLB value for surfactant B. That's the formula we're going to use. And remember, we're going to set the surfactant with the highest value as A. So A is going to be between 20, which has an HLB of 16.7, and B is going to be span 80, which has an HLB value of 4.3. Okay, so this is going to be the HLB mix we're trying to get to is 9.5 minus the value for B, which is 4.3, divided by 16.7, take away 4.3. So that's going to equal 5.2 divided by 12.4, which equals give or take 0.42. So that's the fraction of A we need. And the fraction of B equals 1 minus the fraction of A, which is equal to 1 minus 0.42, which is therefore equal to 0.58. Okay, so that's the fraction of each one that we need. But we need to get to the final mass, and the final mass that we would like is 10 grams. So for this one, I'm going to times that by 10, which is equal to 4.2 grams, and the same here, times by 10, that's equal to 5.8 grams. Okay, let's double check. Does 4.2 and 5.8 equal 10? Yes, it does. They equal 10. So we've got the final mass that we need, and we're putting in more of surfactant B, not by much. So more of surfactant B, so the HLB that we started with, that we were trying to get to, should be slightly closer to span 80, but it should be relatively in the middle. And that's about right. So we've done a sense check on our answer, and we know then that this is the mass of tween 20 that we want, and this is the mass of span 80 that we want. And there's your answers for question 2. And that's what you need to carry on and do for the rest of the questions in there. I've put a good few examples in there because I imagine this is something that a few of you are going to need to do some practice on. And all you need to do is tweak the numbers and see if you can do it. But that's what I've done in there. And if you need them, I'll put up the answers for those if you request it from me, but I'm not going to put them up straight away, because you need to try this sort of thing on your own first and not just rely on the answer, because it's the sort of thing that some of you will just need to practice. Okay, so after that, there's a couple more questions, and the first one is talking about Stokes Law, and the second one is, what does creaming of an emulsion mean, and why is it undesirable? So hopefully you know that creaming is where we get splitting, but the disperse phase goes up to the top, and it's undesirable because if we can't redisperse it, which isn't generally possible with emulsions at home, then we're not going to get a uniform dose out of our pharmaceutical product. Now, the Stokes Law, remember, we were looking at density difference, we were looking at viscosity, and we were looking at droplet size in here. So how would we change them to make an emulsion more stable? Well, we'd make the droplet size smaller, we'd make the viscosity of the disperse phase higher, and we'd try and get the density difference between the two liquids as close to each other as possible. It's kind of the same as the suspensions. But this may change how we treat an emulsion after it's been manufactured. So again, we might think about, could we dilute a formulation? Well, if it was water and oil, no, we couldn't dilute it with water. It would have to be diluted with oil, which isn't what most people would want to do. And we might be adding other things in there that would affect droplet size, and we might crack the emulsion. So that's the sort of thing I want you to be thinking about when you're thinking about these formulations and linking them to your final practice. So have a go at those practice questions, look through the formulas. You only need to know how to use them both. You don't need to do the rearrangement yourself, and see if you can link that to practice. And hopefully you found it useful to be able to actually apply these things in practice by yourselves at home. And of course, any questions, bring them to any drop-ins with me, and I'd be happy to go through it all with you.